Welcome to a general electrical testing engineering technician Tech Bite training series. This training session will cover digital low resistance ohm meters known as DLROs. So why do we use a DLRO? You have two diagrams here, the one on the top and the one on the bottom. In these diagrams, we're using 10 foot of number 12 copper lead wire, which is equal to 1,980 microohms per foot. The 10 feet of lead wire would be 19,800 microohms or 0.0198 ohms. When working with values quite often under 0.0005 ohms, the lead resistance is a significant factor and can produce inaccurate results. The diagram at the bottom uses what we call a voltage drop with the current in order to measure and reduce or remove the resistance of the leads. Bus and connections, we're reading in the microohm range, which 10 microohms would be 0.00001 ohms. Because of these low values, lead resistance is just intolerable. So here you see us checking a piece of bus work on the left. We have two connectors we're using. The connector has a current in one side of the jaw and a potential in the other side of the jaw. The idea is we pass current from one probe to the other, and at the same time we measure the voltage drop so that we're only measuring the actual resistance between the two probes, and the lead resistance has no effect. Here you'll see when we're out on the outer edge of this spliced together piece, we're reading 53 microohms. If you look at the one on the right, we're going to get a little closer together with our leads, and you'll notice it drops down to 42 microohms. This allows us to measure very small values. Now what we're going to see in this series of photographs, the one on the left, you'll notice we've inserted an aluminum lug in between the two copper pieces. This is going to add some additional resistance that we'll be able to see if you look at the photo on the right with our DLRO showing 72 microohms versus the 52 microohms earlier. In electrical power testing, we have to do lots of measurements to measure contact resistances and bus resistances. In this picture here, we see a three-phase bus work. A phase, B phase, and C phase. You'll notice there are two connectors connecting the buses together, and in this one here we're using 1/4 inch by 6 inch bus work. The total length of the bus work is 60 feet long. The bus is copper. What would you expect the resistance to be, not counting any joint connections? How could we test this? We would test it with a DLRO, but this long of a run can get a little tricky. So we're going to see how we would approach this if our leads are not long enough to reach from one end to the next. There is what we call the hard way and the easy way. First, just so you'll appreciate the easy way, let's take a look at the hard way. In the hard way, what we're going to do is we're going to take A phase, B phase, and C phase bus, and we're going to measure these. We're going to measure we're going to jumper A bus to B bus on the right side, and we're going to measure A to B. Then we're going to jumper A bus and C bus together and measure A to C, and then we're going to jumper B bus and C bus together and measure B to C. So we're going to measure A to B, B to C, and C to A, ultimately is what we will do. Now that's going to be two-way resistance. Resistance down one bus, resistance up the other bus. So as far as comparing one bus to the other, this gets a little difficult. The only way to do this with the hard way, and using this method, is going to be to solve for simultaneous equations. What that means is that in this case here, our A to B measurement is 788 microohms. Our B to C measurement is 813 microohms, and our C to A is 825 microohms. So what we do is we take A phase would equal the A to B, which is 788, is A to B minus B. So if we measure A to B and it's 788, and we subtract B from that, then what is left is A. Similarly, it works with B and C phase also. But then you have to start replacing these formulas. So A, that was equal to 788 minus B, we replace B, as we can see in our formula up above, with 813 minus C. So now we got to replace C. And we see in our formula up above that C equals 825 minus A. So now we have three numbers and one letter. So A equals 788 minus 813 minus 825 plus A. In the end, what we end up with is 2A equals 1,613 minus 813 equals 800. 800, since it's 2A, divided by 2 equals 400. Therefore, A is equal to 400, C is equal to 425, and B is equal to 388. This is solving for simultaneous equations. This is not an easy way to do it. It's why we call the hard way. Let's look at a better way. Now let's look at the easy way. In this method, we use the B bus as our C2 lead and jumper the remote end B bus to A bus. This completes our current circuit, so we have current flow through A bus and back through B bus. Then we use the C bus as our P2 lead, and at the remote end, we jumper C bus to A bus. Therefore, we have C1 and P1 on one end of our bus, A, and we have C2 and P2 on the other end of our bus, A, simply using B and C as lead extensions. So what good is testing if you don't know what you're looking at from a result standpoint? When we execute measurements of conductors, we'll evaluate it one of several ways. Not to exceed a maximum value from some manufacturer's specification, no more than an X percentage deviation from a calculation of some comparable value. For instance, the measured value shall not exceed 50% deviation from the lowest value measured. That's a NETA requirement. So how do we get that? In our example that we looked at, we had three measurements of 400, 388, and 425. The smallest measurement is 388. So what you do is you take the measured value, let's say for instance 425, minus the smallest value, which is 388, and divide it by the smallest value times 100 will give you the percentage deviation from the lowest value. So 425 minus 388, the resultant of that divided by 388 will give you 9.5%, which is less than 50% deviation. Try it for yourself. Now let's look at an example that we've put together here real quick. We have here a piece of bus work that has a total of 5 sections. It's 40 inches long, total length, and 5 1/4 by 2 inch copper bus sections, connected with a single 3/8 inch stainless bolt. This bus should be approximately 16.5 microohms per foot. This equates to a total resistance of 55 microohms that we expect. So here we're actually going to measure our piece that we put together. We see that the 40-inch bus piece measures 92 microohms on the right. We expected a base calculation should have been 55 microohms. As a control, we would expect 16.5 microohms for a 1-foot section. Our reading is 18 microohms. If we use this, then we would expect 60 microohms out of our total 40-inch section, based on our overall length. 92 microohms, we should have 32 microohms of connection resistance that's added to that. So let's measure each of the joints and see what we have. The first joint we see here, 1 to 2, is 26 microohms. The next joint, section 2 to 3, is 8 microohms. Our third connection, 3 to 4, is 7 microohms. Our final connection is 16 microohms. Based on NETA, we should investigate any connection of more than 50% deviation from the lowest connection. As you can see with these measurements and calculations, 2 of our measurements would require investigation or are way out of specification. And in fact, they're intentionally tampered with to produce these high percentage deviations. This concludes our tech bite on the digital low resistance ohmmeter, or DLRO. If you have any questions or comments, please send them to steve.newton@nattlefield.com. Have a great and safe day.